That was just in case you have to talk to aliens. We're going to continue our discussion of waves, and in this video lesson, we'll talk about sound waves. In the previous lessons, we've talked about how energy can move through media, solids, liquids, or gases, as a wave, as a sinusoidal wave. We talked about longitudinal waves, which are also called compression waves, and transverse waves, and we showed several examples of how waves can also pass through solids, and we talked about the relevance of that with respect to earthquakes. So in this video lesson, we'll talk about sound. Now, we said that sound was a compression wave, and let's go back and talk a little bit more about that. So when a string vibrates, or a diaphragm or a membrane of a speaker or a drum vibrates, or metal like of a tuning fork or cymbal vibrates, it produces a compression wave of air molecules. The illustration shows a speaker on the left and how it pushes against the air molecules, causing the air molecules to compress in a zone, a compression zone. That then is followed by a dilation or a rarefaction zone where there's a depletion of gas molecules. And so the compressed region of air molecules is what moves along as a sound wave. Now, if you consider the density of the gas molecules and plot that density versus distance, you can see that that is what can be represented as a sinusoidal wave. So the vibration of a string or a diaphragm or metal can produce these compression zones within air molecules that become this traveling compression wave, or the sound wave. In the next few slides, I'll show you some examples of vibrating strings on a guitar, the membrane on a drum, cymbals in a speaker's diaphragm, to show how these instruments can produce vibrations that can be transmitted to the air molecules. What is really fascinating then is that we can sense these compression waves of air molecules. We have these exquisite organs, our ears, some of them are more lovely than others, that can collect the sound waves coming through the air, funnel them into our middle ear. And if you look at this diagram to the right, I show a blow-up of the middle ear, which includes an eardrum, a membrane, which then is connected to three very small bones. These are the smallest bones in our body. They're called ossicles. We typically call them the hammer, anvil, and stirrup. These three small bones, which are connected to the eardrum, which senses the vibrations of the air molecules, which are then produced by whatever is causing the sound. So the three bones will begin vibrating, and that then transduces a signal to our inner ear, where we have nerve cells that include some hair-like structures that can sense the frequency of the sound and thus transmit that signal to our brains, which we then recognize as sound. There is a YouTube video, which I've included the link. I won't show that in this video lesson, but it is a very nice video showing how your ear works. Now let's talk about sound and music. And let's apply this equation that we talked about earlier, the linear velocity of the propagation of sound, v, velocity. Again, for sound moving through air, that velocity is 340 meters per second. That velocity is equal to the product of the wavelength, lambda, times the frequency. Let's apply that to an example of a pipe organ. Let's say that middle A of a pipe organ has a frequency of 440 hertz. What then is the wavelength of the waveform or the vibration associated with this 440 hertz? To calculate that, we take the above equation and we simply rearrange it, a sleight of hand, but very little sleight of hand, and rearrange for lambda, which is then equal to the velocity divided by the frequency. So the velocity 340 meters per second, the frequency 440 hertz. A hertz is a reciprocal second, or second to minus 1. If we just plug this into our calculator, we get 0.773 meters as the wavelength. Now that's a little over 2 feet, maybe about like that. That would then be the wavelength of a sound wave corresponding to 440 hertz. And our ears can respond, can sense compression waves in the air that have a wavelength of about 2 feet. Now humans can hear sound with a frequency that ranges from as low as about 20 hertz to as high as about 20,000 hertz. So about a 1,000-fold range in the frequency that humans can respond to. Other animals can respond to a broader range. I find it a little difficult to think about this in terms of hertz, and it makes more sense to me to convert this to wavelengths because I can see distance. So the 20 hertz corresponds to 17 meters. 17 meters is nearly 2 first downs in football. So humans can respond to sound waves as long as almost 2 first downs in football, 17 meters, and as short as 0.017 meters, which is 1.7 centimeters, which corresponds to a frequency of 20,000 hertz. Now, 1.7 centimeters, if you remember your pinky, the width of your pinky is about 1 centimeter, so about almost 2 pinkies worth of fingernail would be the shortest wavelength. So our ears can sense these compression waves that are as long as spread out as almost 20 yards or 17 meters and as short as 1.7 centimeters. This slide shows this range of the human hearing from 20 hertz, 17 meters or so, to 20,000 hertz, 1.7 centimeters, and relates that to the piano and shows also the frequency range of male voice, female voice, and various musical instruments. Thought you might find that interesting. Also, I have another link which you might try, and this is a tone generator that you can type in the frequency like 500 hertz, and it's a free online tone generator. So you can see what different frequencies sound like and see how low a frequency or how long a wavelength you can detect or how high a frequency or short a wavelength you could detect. In the next few slides, I want to talk about some additional properties of sound waves. Actually, these properties apply not only to sound waves, but also electromagnetic radiation, which we'll get to in the next video lesson. But for sound waves can be either additive in ways that are constructive, that is, they add together and increase the amplitude of the sound, or they can be destructive. Now, the constructive addition of sound seems obvious to us. If you have 2 waves, such as shown in the left, and if you add them together, that is, if you had 2 speakers, you would imagine that you would double the amplitude of the sound that would be produced. What is a little bit harder for us to understand, however, is that 2 sound waves can also destructively interfere with each other to the extent that they could actually cancel each other out. Now, this canceling is hard to achieve to get exactly lined up, but 2 sound sources can interfere with each other in ways that are destructive so that the total volume is much less than the sum of the 2. Those 2 examples of constructive interference and destructive interference apply if the waves have the same frequency. More often, we add waves together that have different frequencies, as shown in the right example. And when you add 2 waves that have different frequencies or different wavelengths, what you get is just a gamish. You just add it together, a cacophony. Another effect I want to talk about related to sound but also light is something called the Doppler effect. Now, the Doppler effect refers to the fact that if a source of a sound wave is itself moving, that the velocity of the moving emitter adds to the velocity of the sound itself, resulting in a higher frequency sound as the emitter of the sound, like an ambulance, is approaching a listener, and a lower frequency of sound as the emitter moves away from the listener. Now, these are also sometimes called blue shifts and red shifts. So if you have a train approaching you with its blowing its whistle, and if it's approaching you very rapidly, the velocity of the moving train plus the velocity of the sound would add together, giving you an apparent higher frequency or blue shifted sound. And as the train passes by and moves away from you, it appears as if the sound being emitted is a lower frequency, longer wavelength, or what we call red shifted. Now the police also use the Doppler effect to determine if we were speeding, and I had an unfortunate experience with that not too long ago. To the right, we see our friend Sheldon, and he was dressed for a costume party, and of course he came dressed as the Doppler effect. And I'll show you a little video in case you missed it.
What's Sheldon supposed to be?
Oh, he's the Doppler effect. Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay. See? People get it.
Okay, people get it. So here are just a couple of illustrations of the Doppler effect. Again, the train moving towards us, the frequency of the sound produced seems to be a higher frequency or a blue shift, whereas if a train is moving away from us, the sound produced seems to have a lower frequency or be red shifted. Another example would be the ambulance moving towards us. It appears to have a higher frequency, moving away, a lower frequency. In the next little video, I'll actually show you a YouTube video of a train approaching, and you can hear the difference in the pitch or the frequency of the sound as it approaches you and moves away. Okay? Don't be frightened by the sound. Okay, we're going to pause and take a little quiz. And then when we come back, we'll move into electromagnetic radiation, or light.